Okay. Now, what I want to do is, for the last lecture, we're going to cover an electrocyclic reaction, and then we're going to cover some sigmatropic rearrangements, specifically sigmatropic alkyl and hydrogen shifts. And so let's start off with the electrocyclic reaction. If you take 7-dehydrocholesterol, you can open up this ring in an electrocyclic reaction. To give this product right here. So for this reaction, what do you need? Do you need heat or do you need light? Go ahead and pause it to figure it out. I'm going to go ahead and figure it out right now. I'm going to start by drawing in the important bits. We have this. And we have the methyl group going up and the hydrogen going down based off of the original stereochemistry. Essentially all I did was I rotated this 180, well, not quite 180 degrees, but a little bit more than that, because I like having the bond that we're opening towards the bottom of the page. That's opening to give this structure, with the methyl group and the hydrogen both going inwards. So the hydrogen starting out down, the methyl group is starting out up. Hydrogen's going to the right, the methyl group ends up going to the left. And so this hydrogen was rotated counterclockwise. This methyl group was rotated counterclockwise. And so this was a disrotation. Excuse me, not disrotation. They're both going the same direction, counterclockwise, counterclockwise. It's a conrotation. Excuse me on that. And since it's a conrotation, we're going to bring up the Woodward-Hoffman rules. 4n plus 2, heat, light. And so heat, 6 electrons, that's the disrotation, and superficial, dis, superficial, 4n electrons, con, ter. So here is Woodward-Hoffman rules, and when we look, we are actually moving 6 electrons. So 6 electrons, conrotatory, so this is light. So we need light to do this reaction. Okay. Now, this molecule, it turns out, is unstable. It will rapidly do another reaction, and it will do so in the dark even. So it's a thermal reaction where this hydrogen migrates to here, These electrons go here, these electrons go here, these electrons go there. And you get this molecule here. Just making sure all my bonds are correct. Yep. This molecule just happens to be vitamin D3. Okay, now this reaction of irradiating, creating vitamin D3, is of particular importance to the University of Wisconsin because of Harold Steenbach. You might be familiar with his last name. There's a restaurant named after him. There is a library named after him. But essentially, he's one of the reasons, actually, if not the reason, that Wisconsin is the research powerhouse it is. Because what he did was, when he figured this out, he was offered a lot of money for the patent of it. But instead of selling off the patent, what he did was he created what's called the Wisconsin Alumni Research Foundation with a few others. And it used the money, the proceeds of the patent for this reaction right here, to fund further research at the University of Wisconsin. And that money goes for patenting technology at the University of Wisconsin. And then it patents it patents research and discoveries at this university, and then proceeds from those patents are then fed back into WRF and fed back into the university, which patents more, and it keeps building up, and essentially it has paid for a lot of the research that takes place on this campus. So you can read out more about WRF. One of Harold Steenbach's last graduate students, he stayed on at the University of Wisconsin, further looking at vitamin D and as well as derivatives of vitamin D. And his last grad students, one of his last grad students, his name is Hector DeLuca, and you might have heard of his name as well, because there seems to be a couple of biochemistry buildings on this campus named after him. And so, hugely important to this university. But what I want to talk about is the reaction right here. It's a thermal reaction. It uses 4 arrows, so it's 8 electrons. 8 electrons is a 4N reaction. It's under heat, and so this is what's called an interfacial reaction. And the name of this interfacial reaction, it's a sigmatropic rearrangement. And when we name sigmatropic rearrangements, we simply number on each side of the sigma bond, and then count to where it ends up going. And in this case, what we end up doing is getting what's called a 1,7 shift, because the new bond appears between atoms 1 and 7. Okay. Now, if you were to try this 1,7 hydride shift, say had this molecule here in deuteriums, and you heated it up, no reaction, at least no 1,7 deuterium shift. Doesn't work. But if you go with a smaller ring, say a 5-membered ring, heat it up, and the thing is, this is set up to do the same shift. It could be a hydrogen shift, it could be a deuterium shift, and it just keeps going and gives you a mixture of isomers. This one would be a 1, 1. We got to encircle all of the arrows. This would be a 1, 5 shift. Now this 1, 5 shift, though, is possible. Because it is a superfacial rearrangement. Has 6 electrons. But this one right up here, it doesn't work. So, let's talk about the differences between these and why this one would work in an open chain but not in a closed chain. So let's sort of break this down to the simplest components. Deuteriums to migrate. This. And we heat it up. So it's a thermal reaction. Thermal reaction means we're going to be using the HOMO, the highest occupied molecular orbital. Like so. Now, what I've done, what you need to do is draw in the HOMO, and this is just of the pi system right now. Okay. Now, this is the pi system. We need to also draw in this carbon right here. And we are going to approximate this carbon as kind of a p orbital, or an sp3 orbital if you want, like so. And let's get the shading right. There's not a pi bond between these two, and so when we're shading it, we're going to shade it like this. We're going to not worry about the deuterium yet. Now that deuterium, picture that as going either on the top lobe or the bottom lobe. It doesn't matter, and there's a bond to it. So I'm going to draw it on the top lobe. Shaded. Now, in order to do this reaction, the bottom lobe here has to grab it because that bottom lobe is shaded in the same shading as the p orbital, as the deuterium, as that s orbital is. And so, as a result, this molecule has to start off with the deuterium on the top, and it would end up on the bottom. And the way that works is this molecule itself is not planar. The single bonds are rotated just enough. So think about it this way. Take your pen and balance it on the top of your right hand. Then what you can do with your left hand is just pick it off your right hand. You're using the top of your right hand and the bottom of your left hand to transfer that pen. That's an interfacial process. Now, if you link your thumbs together in a ring, you can't do it. Well, at least you shouldn't be able to do it. You'd have to break contact with your thumbs in order to get it from the top to the bottom. Yes, I know there are problems with that analogy, but that's what I've got. So, that's why it's interfacial. It started out on one side, it ended up on the other. And when you have a closed ring, the reaction doesn't work because you can't lift that top p orbital up enough to grab it. Now, if we do a 1,5 shift. To draw the orbitals there, start by drawing the pi system. And then we approximate the new carbon as a p orbital. And then we draw a deuterium in. I'm going to draw it on the bottom. There's no pi bond between carbon 1 and 2, so I'm going to shade it appropriately, like so. Now if you take a look, this is shaded. It starts out on bottom. And it's shaded. This is the orbital that's going to take it, because it's also shaded. It ends up on bottom. So if it started out on bottom, ended up on bottom, that's a superfacial process. And so this would be the equivalent of just moving the pen from the top of one hand to the top of the other. And if your thumbs are linked, you can still do that. It doesn't pass through that bond at all, breaking your thumbs. Yeah, that analogy was more violent than I thought it would be. So anyway, you kind of get the picture. If there's a bond here, that doesn't interrupt the fact that you can go from the bottom to the bottom or the top to the top. It stays on the same face. So let's do a problem with this. So an example might be something like this. So you start with this optically active, you heat it up, and the deuterium transfers. And you end up getting a mixture of these two products that are optically active. And the stereochemistry of these two are dependent on the stereochemistry of this. What I mean by that? First of all, the reaction is these electrons go here, these go here, these go here, those electrons go there. So it's 8 electrons. It's a thermal reaction. It's a 8 electrons thermal reaction. That's an interfacial reaction. And so if we rotate this molecule, this carbon-hydrogen bond right here, so that deuterium is a wedge, you get something like this. This is an s chiral center. Notice this is still an s chiral center. When that deuterium shifts over, to there, it's an interfacial process. It started out as a wedge, so going on the top, then it's going to end up being a dash on bottom. So as a result, that stereochemistry is going to be an R. And so this one right here is going to be an R. I matched that to that. And I have one too many carbons here, I see. No, I don't have one too many carbons. I am missing an alkene. That's my problem. So that's an R. That means that right there is a dash. That's a wedge. But we could have also rotated that deuterium so it's a dash. And when we do so, get that. Again, we can have the reaction. But since it started out as a dash, that deuterium now is a wedge. It's going to come from, started on the bottom, so therefore it ends up on the top. And this is an s chiral center. So therefore, this is going to be an s chiral center. That deuterium would be a wedge. So the important thing to do when you're doing this is figuring out its anterofacial or superfacial. And if it started out on one side and it's anterofacial, then it ends up on the other. If it's superfacial, if it starts out on top, it stays on top. If it's anterofacial, if it starts out on top, it ends up on bottom. Okay. Any questions? Well, that sounds silly. If there's questions, please put them up on Piazza and I'll do my best to answer them. Okay. So we actually had some of these sigmatropic rearrangements in Chem 343. An example there is a carbocation rearrangement. So this is an example of a 1-2 shift. The number of electrons that are flowing are 2 electrons. 2 electrons, that's superfacial. So it's allowed. Carbanions do not rearrange. Because this would be a 4-electron process. Four-electron process would be anterofacial. Now, I don't know if you can rearrange a carbanion with light. That's a little tricky to study, but I suppose it's possible. But right now, when it comes to sigmatropic rearrangements, we're just worrying about thermal ones, not the light ones. Another reaction that we talked about is tautomerization. You might think about drawing the mechanism this way to giving that product. Well, because then that would be a 1, 2, 3, 4, a 1-4 shift. but it's a 4-electron process. 4-electron process is antifacial, and this is too small for an antifacial reaction. You need to really have at least 3 pi bonds in an unopened, so at least 3 pi bonds in a straight chain in order to have an antifacial reaction. This is way too small. Therefore, tautomerization is not a concerted reaction. Instead, tautomerization is a 2-step reaction, where if you're an acid, you protonate first, and then you deprotonate. If you're on base, you deprotonate first. And then you protonate. But it's 2 steps, not concerted. Because if it was concerted, it would be antifacial, and that's too small to do an antifacial reaction. Okay, that's pretty much all I have. We've covered everything that we wanted to cover for this course. Thanks for taking this course in trying times, and organic chemistry probably made things a little bit more trying, but I appreciate your patience with the process and wish you the best.